aperiodic structures, like the one that you can see on the left-hand side, where we have a spiral arrangement of air holes on a freestanding membrane. And what I will show you is how we can use such structures to confine light. So this is an example of a photoluminescence image that we've taken from one of these devices, where you can see that light is trapped, and with various degrees of quality that we will discuss. And I will also show you how we can use these devices to control the spontaneous emission rate of single photon emitters. So I will start with a very brief introduction on why we're interested in quantum photonics. I'm sure that, I mean, I don't need to explain it very widely to this audience, but the idea is that if we are able to control single photon emission and propagation, we can encode information in the single photons. So this is a resource for quantum communication, where we can have information that travels at the speed of light. It can be secure against eavesdroppers if we implement, for instance, quantum cryptography protocols. And in general, quantum light can be seen as a resource for a variety of quantum technology applications. And for instance, it can be used as an interface for quantum memories, or in general to connect different qubits for instance, quantum computation schemes. And so in general, we can see the application of single photon sources in quantum key distributions, in linear optics, quantum computing. We can do imaging with single photons or entangled photons, and we can use this quantum light in order to obtain, for instance, to go into the field of quantum sensing, including more accurate position navigation and timing. And so for all this, if we want to have a reliable way of utilizing these quantum light sources, we need some key characteristics, which include on-demand generation. So we would like a system that will emit a single photon every time it's triggered. And we want to be able to control the brightness into a desired collection channel. So we want to be able to guide the light into a specific optical mode. We want to make sure that every time we trigger our source, we get one and only one photon. So we want to suppress multi-photon probability in the emission process. And for certain protocols, we also want the light to be indistinguishable. So we want all photons to be identical in all their parameters. And ideally, if you're looking at, well, any of the applications, but for instance, if you think of communication, you would like to have the highest rate of information per second possible. So you want a high emission rate, which implies a short lifetime in the recombination process. I mean, this is true for communication, but it's also true for instance, imaging or any sort of experiments that you would like to do. You would like to have the highest number of photons emitted per second so that you can increase your signal-to-noise ratio. So there are several different systems that can act as single photon emitters, but the one that I will focus on today are self-assembled semiconductor quantum dots, which are, in our case, based on 3-5 materials, so gallium arsenide, indium arsenide. So the advantage of these sources is that they can be grown directly on a semiconductor chip. Therefore, they are compatible with the existing semiconductor technology, and we can also fabricate photonic devices using nanofabrication techniques. So our quantum dots are grown by molecular beam epitaxy. So we start with a gallium arsenide substrate, where in this case, gallium arsenide is schematically shown by these blue spheres. And then in ultra-high vacuum, single monolayer of indium arsenide are grown on top of gallium arsenide. So indium arsenide has a different lattice constant than gallium arsenide. So the first monolayer we grow strained. And after that, after a certain critical thickness is reached, it will no longer be thermodynamically favorable for indium arsenide to grow strained. And we will have the formation of these nanometer scale islands of indium arsenide that we then recap with gallium arsenide. So you can see from this transmission electron microscope image that we get this sort of lens-shaped nanostructures, which are about 20 nanometer in size. So given that we have a structure where we have gallium arsenide, indium arsenide, and gallium arsenide, thanks to the difference in band gap within the material, we create a three-dimensional confining potential, which gives rise to discrete energy states. and therefore discrete-to-discrete energy transitions can give rise to the emission of single photons. So these have been described as artificial atoms, but of course they are much more complex than isolated atoms or ions, because while they are composed by more than 10 to the 4 atoms, but also they are within a semiconductor system, so they can interact with the environment. But overall, they're shown to be very stable sources of quantum light, which can provide good brightness and coherence in the emission. So now I will give you a brief recall on what a photonic crystal is, because it's it's at the basis of the devices that we'll discuss later on. So we are looking at two-dimensional membranes. So we have a freestanding membrane of a semiconductor. So we have air on both sides, which implies that the light is confined in the vertical direction by the refractive index contrast, so by total internal reflection. And then in our photonic structure, what we do is that we etch a series of air holes which modulate the refractive index. So we get a periodic modulation of the refractive index, for instance, between gallium arsenide and air. And this results in the opening of a photonic band gap. So what this means is that there will be this periodic modulation of the refractive index results in the fact that certain frequencies of light will not be allowed to propagate in the structure. So this is similar to what happens in semiconductors, where we have a periodic potential due to the crystalline structure that results in an opening of band gap, and therefore a range of energies that the electrons cannot have when propagating in the structure. So why is this important? Because what we look at are how this modulation of the density of optical states created by this photonic band gap will affect the spontaneous emission rate, which is one of the critical parameters that I was discussing earlier in terms of the implementation of single photon sources, and also how we can use this photonic band gap to guide light, so to control how light propagates, for instance, in specific optical modes, and how we can trap it in a small volume, high quality factor cavities, and therefore enhancing the light-matter interaction. So these are examples of how photonic crystals can be used in photonic devices. So what you can see here, for instance, is a periodic arrangement of air holes, and then a defect is introduced, so a hole is removed. And if you have an emitter which is emitting in the defect region at a wavelength that is within the photonic band gap, the light will not be allowed to propagate within a photonic crystal structure. So it will be confined in a small area, and therefore you will have a small mode volume cavity which can reach a very high quality factor. So light can be trapped for a very long time within these structures. Or you can introduce line defects which act as waveguides, so the same principle. So the light will not be allowed to propagate in the photonic crystal region, so it will only propagate along the defect, and in this case, along a one-dimensional channel. So we can control where light is trapped and in which photonic modes it will propagate by engineering these photonic crystal structures. So this is all fine. There's been a lot of work that has been done in this area, and but there are some issues related to these photonic crystal structures. So first of all, so you're all familiar with a natural photonic crystal, let's say, which is what you can find, for instance, in the wings of butterflies, and that what creates this iridescence is a periodic modulation of the refractive index. But what we're looking at are highly engineered structures, where I was saying you can remove a few holes, create defect regions, and therefore have light trapped within the areas where the holes have been removed. So this works well, but what has been shown already, more than 20 years ago now, is that these structures require nanometer scale accurate fabrication processes, which means that if you, for instance, so these are relying on the quality of the confinement relies on the position and shape of the holes close to the defect region. So if you slightly perturb this by, for instance, moving the holes over a few nanometers, what happens is that the frequency of the confined optical mode shifts, and also the quality of the confinement, which is directly related to the line width of your cavity modes, can change abruptly. What this means is that it's hard to scale, to reproduce the results obtained with this photonic crystal structure. You simulate very high quality factors, but then you fabricate your devices and you get a distribution of these modes, and you cannot really obtain the high values that you reach in your simulation. So scalability is an issue. So what we'll be looking at are ways to overcome this. So can we have a photonic crystal structure that allows us to have the good qualities, therefore high quality factor, for instance, in the confinement of light, and high flexibility in the way light can propagate in your structure, but creating systems which are less that require less accurate fabrication processes, and therefore that can be more scalable. So I will now define some sort of like three classes of photonic crystals. So the one that I've just discussed, I will call it the periodic photonic crystal, or if you like, the highly engineered structure. And then we have the opposite range of the spectrum, which is a disordered photonic crystal structure, which is something we have been working on in the past, which is, for instance, in this case, what we have is a photonic crystal waveguide. So we have removed roller holes. We have a sort of one-dimensional system for the propagation of light, but then we introduce disorder by perturbing the position of the air holes with respect to the perfectly periodic structure, which is shown by the red circles. So the fabricated holes are randomly distributed around the position where they should be in the perfectly periodic system. And what we are showing is that such a device allows us to reach Anderson localization of light, and light will no longer propagate along the waveguide, but can multiple scatter on the different imperfections and be trapped in sort of closed loops, which represent our Anderson localized cavities in a disordered photonic crystal structure. But I will not discuss about this today. I will talk about an intermediate regime, if you like, where we are looking at aperiodic photonic crystals. And the advantage of these structures is that, amongst other features that I will discuss later, is that the confinement of light relies on the long-range order. So the long-range aperiodicity, which is created in this case by etching air holes in a sort of spiral patterns. So given that the light confinement is no longer related to the accurate position of a few air holes and their shape, these structures are inherently more robust to fabrication imperfections. Okay, so now I would like to focus a bit more on the properties of these aperiodic structures. So they've been studied in the last, I don't know, 10, 15 years, mostly, well, to my knowledge, in passive devices. So systems where light was either reflected or transmitted through. And what has been shown is that you can have a polarization insensitive light diffraction. And these structures can sustain omnidirectional photonic bandgaps, and they can also impart optical angular momentum on light. So this is an example of a device where, for instance, metallic particles have been deposited with this sort of aperiodic arrangement, or this is a similar structure as ours. So you have well, so these are the simulations of the modes that can be sustained by this sort of aperiodic structures. So the applications are the usual applications that we can realize when we increase the light matter interaction. So we can do optical sensing, we can do photo detection, optical imaging, and enhanced second harmonic generation. So what we did differently is that we investigated active devices. So we looked at aperiodic photonic devices where we have internal light sources, which can be classical light and quantum light. And I will show you two examples of this. So the first one is a device we have fabricated in silicon nitride. And what we have grown silicon nitride with the defects inside. And these defects emit in a wide range of wavelengths. As you can see from this photoluminescent spectrum, we have emission between about 600 and 800 nanometers. So we can, so the silicon nitride, once illuminated, will emit with this broad spectrum, and we'll use this broad emission as the internal light source, this classical light, to investigate how light is trapped and confined by our aperiodic structures. So it's a silicon nitride system. So we are operating in the visible at room temperature, and we use standard silicon nitride nanofabrication processes. And then we fabricate a freestanding membrane of silicon nitride with this arrangement of air holes in this spiral pattern, which follows a Fibonacci series that can be found, for instance, in the arrangement of seeds in sunflowers. So this is fabricated with electron beam lithography and KOH, well, dry etch and KOH wet etch. So it's a freestanding silicon nitride membrane with air on both sides. So then what we do is that we look at photoluminescence images to visualize the confined optical modes. So this is a schematic, well, a very simplified schematic of our setup. So we are illuminating, it's a confocal microscope. We are illuminating, in this case, with a 455 nanometer light emitting diode, our sample, which is sitting on a translation stage. We focus down the LED light with an objective, and we collect the same objective, and then send the emitted light onto an EMCCD camera. And what this setup allows us to do is to illuminate a sort of like wide area. So it's about 50 by 50 micron in size. And what you can see here is a photoluminescence image superimposed to our scanning electron micrograph image of the fabricated device. And what you can see is that you have a light confined mostly in the center of the structure, and then you have this sort of more extended modes. So we have first proof that there is light confinement in our structures, and then we can slightly modify our setup. We introduce a 4 or 5 nanometer continuous wave laser, and instead of sending the light to the EMCCD camera, we send it to a grating spectrometer, and we take spectra with the silicon CCD. So what we can do now is that we can focus our laser on the areas where we have observed the confined optical modes in the photoluminescence images, and have a spectral signature of our optical resonances. So what you see is that we have multiple peaks, which are the signature of light confinement, the spectral signature of light confinement in our cavities. And then we can look at, for instance, the quality factors to evaluate how well light is trapped within our cavities, and we see quality factors up to 4,600, which are actually not too bad considering what quality factors are obtained in photonic crystal cavities in silicon nitride in the visible. So we are confining light with relatively high quality factors in these silicon nitride structures in the visible in ambient conditions. So then we can look at what parameters can we vary to control this light confinement in terms of like wavelengths and in terms of quality factors. So what you can see here are the wavelength for the confined optical modes and the measured quality factors when varying the diameter of the air holes in our structure. And what you can see is that by changing the diameter, you can shift the wavelength range where these modes appear, and you can also have a variation in the quality factors. So these are degrees of freedom that we can adjust. And what you see on the right-hand side is our log normal distributions of the quality factors, depending again on the diameter of the air holes. So this all works fine, but this was all classical light, and something that, well, I started with was saying that we wanted to work with quantum light sources, but also that this structure supported a band gap, which can be used to modify the spontaneous emission rate, which is one of the key parameters that we want to be able to control in our photonic, well, quantum photonic devices. So what you see here are simulations of the density of optical states and of the wavelength of the light trapped in our structures when we vary, in this case, the diameter of the air holes. So what you can see is that given that you have a band gap, we have a reduction of the density of optical states, which is shown here. And by varying the diameter, we can tune where this band gap occurs. And in particular, what we want to do now is to work with our indium arsenide, gallium arsenide quantum dots, which have emission wavelengths in the near infrared. So now we are targeting the 900, 950 nanometer range, and we change material system to gallium arsenide so that we can utilize our indium arsenide quantum dots that I briefly described earlier. And this is our new setup, which is well similar to what we had before, except that we have changed wavelengths now to be in the near infrared. Our sample is now in a cryostat because these indium arsenide, gallium arsenide quantum dots operate around 10 Kelvin. And we also added avalanche photodiodes to be able to do single photon counting, and in particular, time-resolved measurements. So then we fabricate our devices, this time in gallium arsenide, and this is a scanning electron micrograph image. Again, it's a gallium arsenide, 190 nanometer thick gallium arsenide freestanding membrane. And if we look at the simulations of the confined optical modes, you see that we have this sort of annular extended modes. And then we can do photoluminescence imaging of the confined optical modes in our fabricated devices. What you can see is that we obtain this sort of extended modes. Some look similar to the simulated ones, some a bit more complicated, but well, it's a fabricated device, so I think it can be expected that they're a bit more complex than what we expect from simulations. Okay, so some of the symbols have changed, but what I wanted to do now is just briefly recall how we can modify spontaneous emission rates of two-level systems in this case. So what we are doing now is we are looking at time-resolved measurements where we excite with the pulsed laser source, and we look at the intensity of the emitted light as a function of time after excitation. And we'll have the emitter with a certain frequency omega at a certain position r, and we're looking at the emitted intensity as a function of time. Now, what we know is that what we'll have is that we'll have an exponential decay, which is governed by a quantity delta, which is our decay rate. So what we expect to observe is an exponential decay of the intensity as a function of time, and we can then fit it and extract the lifetime or the decay rate, if you like. They are one the inverse of the other. Okay, getting weirder, but anyway, so what is important is that the decay rate is not an intrinsic property of the emitter only. So it depends on parameters that are proper to the emitter, like the emission frequency and the dipole, but they also depend on rho, which is our local density of optical states, meaning that the photonic environment will affect the decay dynamic of our single photon emitter. And what we want to do is that we want to control this optical density of states by, for instance, modifying, by utilizing the band gap, which can be created by our photonic crystals, to then control the decay rate of our emitter. And this is what we are showing here. So this is a spectrum of an indium arsenide quantum dot. You see these atomic-like emission lines. And then what we do is that we look at quantum dots emitting at different wavelengths, and we look at the emission dynamics for different frequencies or wavelengths. And what we know is that these quantum dots, when they are not in a photonic device, they have a typical lifetime of about 1 nanosecond. What we observe is that if we pick an emission wavelength, which is in the band gap, we can measure lifetimes up to 10 nanoseconds. So we are slowing down the emission process because we have reduced the density of optical states. We can we can pick emission lines which are in areas where the density of optical states is increased, and we measure lifetimes down to 500 picoseconds. So what this shows is that our aperiodic photonic devices allow us controlling the spontaneous emission dynamics of single photons. So to summarize, what we have shown is that we can fabricate aperiodic photonic devices with relatively high quality optical cavities. And in general, these structures are less sensitive to fabrication imperfections because they rely on a long-range order as opposed to standard highly engineered photonic crystal devices. And what we've shown is that we can control the spontaneous emission rate, so we can porcelain enhance or make the lifetime longer by utilizing this band gap that is supported by the aperiodic structures. So what we want to do next is we want to scale. Well, we've shown that it works in the visible and near infrared. We now want to scale to different wavelengths, for instance, going towards telecom wavelengths. And as I was mentioning earlier, we can use this structure to impart optical angular momentum on light. So what we would like to do is to use this optical angular momentum as an extra degree of freedom, for instance, to encode the information, or in general to manipulate, well, to illuminate objects, for instance. So not just controlling how the quantum dots emit, but also how the light propagates off the chip. And given that we have relatively high quality factors, we also want to investigate the potential of realizing aperiodic lasers, which might also have encoded optical angular momentum in their properties. So with this, I would like to conclude. Thank you for your attention. Thank the Liverpool Trust for the financial support. And well, you can't see the first line, but we still have open postdoc and PhD positions if anybody's interested, not just in this project, but in general, integrated quantum photonics. So thank you.
Okay, thanks. Any